Hi, I'm Ryan Benowitz, and I'm going to be presenting on evolutionary rule-based machine learning. I'm going to talk about a specific evolutionary rule-based machine learning algorithm called ExSTraCS that my lab developed, specifically designed for the challenges of data mining in biomedical data. So first, let's talk a little bit about biomedical data. It comes in many forms, such as electronic health records, genomic data, but also images like X-rays. It can also come in the form of natural language text, such as doctor's notes, or it can be time series data, such as heart rate, breathing rate, or EKG information. Some forms of biomedical data are already in a tabular format, and we can additionally employ methods such as feature engineering or feature learning to create new columns for a tabular data set. Other types of data, such as images, natural language text, or time series data, isn't already in a structured tabular format. And so to use most machine learning algorithms, we need to first employ feature extraction techniques to pull features out of the raw data and into the traditional tabular data format. Here's a simple illustration of a tabular data set. The rows are instances of the data, and the columns are mostly features and an outcome of interest that we're trying to predict. Let's talk a little about the goals that we're typically going after when employing machine learning on biomedical data. First off, we're interested in identifying risk factors or biomarkers of health outcomes. This can be to understand the cause of disease, to make diagnoses or predict outcomes, or to better target personalized medicine. We might also want to develop a prediction model that we can deploy in a clinic, and we might do this with the goal of making more accurate predictions, or to improve general clinical efficiency. However, there are a number of typical challenges that we have to deal with when working with biomedical data. Some basic challenges include the possibility of having missing data values, having imbalanced data, or dealing with very large scale data, especially when we're combining variables across many different data sources. Regarding signal detection, we might also have to deal with having very noisy signal. Furthermore, the patterns in data can be very complex. As illustrated by this figure, we're often trying to connect predictive features of different types with some outcomes or phenotypes of interest, so that we can make predictions on these outcomes. And the relationships between these variables can be simple univariate ones. We can have a single feature influence many outcomes. We can have multiple features interact with one another in a complex way that uniquely predicts outcome. Or it can have different risk factors or combinations of risk factors that are relevant to only certain subgroups of instances in the dataset. Or in real-world problems, it could be some complex mess of any of these. Furthermore, in biomedical research, it's often the case that we care a lot about interpretation. Is our model transparent and interpretable? And can we reproduce our results or findings? Moving forward, I'm going to be talking mostly about learning classifier systems as a specific family of evolutionary rule-based machine learning methods. I became interested in rule-based methods such as learning classifier systems since they seemed well suited to detecting complex patterns in data, and I was interested to see if they could be adapted to the unique challenges we just discussed that are common in biomedical data. Some of the early research we did was basic proof of principle, seeing what types of basic, already established learning classifier system algorithms were best suited to detecting complex patterns in simulated genetic data. Specifically, we focused on complex associations including epistasis and genetic heterogeneity. And in this paper, we developed statistical and visualization methods to help interpret the rule population being discovered by a learning classifier system. Addressing the problem of large feature spaces in biomedical data, we also explored ways to utilize expert knowledge, which might come in the form of prior domain knowledge, or in the case of this paper, leveraging a feature importance estimation algorithm that was sensitive to interactions, called rebate, to help seed and guide a learning classifier system to better solve complex problems in noisy data. Being particularly interested in the problem of characterizing heterogeneous subgroups in data, pretty early on we developed a novel methodology called attribute tracking, designed to be used within a learning classifier system framework. Basically, the way this works is that during the course of learning classifier training, for every individual instance in the data, we collectively track and update the importance of every feature involved in correctly predicting the outcome for that individual. This idea was inspired by ant pheromone trails. Here on the right is an illustration of attribute tracking scores that are collected during the course of training a learning classifier system on some simulated data with patterns of both epistasis and heterogeneity. The yellow signature indicates features on the y-axis that were most predictive of outcome in this particular subgroup of instances, where instances are across the x-axis. We can see a distinct two-feature epistatic interaction relationship in one subgroup of the patients, and a separate two-way interaction that was modeled in a separate heterogeneous subgroup of the dataset. Here you can find a couple papers we've published on this topic. Adding this attribute tracking concept to a learning classifier system designed for supervised learning, we published this paper applying that algorithm to a small bladder cancer dataset in search of genetic heterogeneity. And in this analysis, we found these attribute tracking scores, where one major subgroup illustrated a signature of a two-way interaction between two DNA repair SNPs, and a separate larger group was identified where pack year smoking was the most important variable for predicting their outcome. Of note, we didn't know these two subgroups ahead of running the algorithm. We then took those two candidate subgroups and put them on a survival curve to see if subjects that belonged to one group or the other had a significant difference in survivorship, which we indeed found to be the case. All this previous work led us to building the ExSTraCS algorithm, a learning classifier system tuned primarily to handle the challenges of biomedical data. The algorithm here is very similar to a basic supervised learning classifier system, but we added a few of the key elements I already mentioned to help ExSTraCS excel in particular in noisy biomedical data. First, we added the attribute tracking algorithm, and this collected information about what features were important strictly from rules that emerged in the correct set every single iteration. And at the end of running the algorithm, we can output these scores. ExSTraCS also leverages these improving attribute tracking scores over time to further help guide the genetic algorithm probabilistically during training iterations. And this was found to further improve algorithm learning performance. The covering operator, which is responsible for initializing rules in the population, was adapted to allow for using expert knowledge guidance, as alluded to in some of our previous work. In particular, we used relief-based algorithms from our rebate software, which could quickly evaluate a dataset and rank features based not only on their univariate association with outcome, but their involvement in epistatic interactions with an outcome. By using this prior knowledge, we can initialize our rule population with rules that are more likely to be useful for predicting outcome. Furthermore, in ExSTraCS, we introduced a very simple rule compaction algorithm called quick rule compaction that simply removed rules that were inexperienced or clearly poor, finding that this too improved overall performance. And last but not least, we also included an efficient rule representation that made scaling up to larger datasets a lot easier, as well as a rule specificity limit, again targeting the issue of scalability of the algorithm. You can find the first paper on the ExSTraCS algorithm here, and a second paper conducting a deeper dive into an extended ExSTraCS framework right here. One of the traditional ways to evaluate learning classifier systems has been using multiplexer problems as a convenient benchmark. These problems are simulated to have a clean signal, but they represent a multivariate, nonlinear or epistatic, and heterogeneous pattern of association. Let's explain these benchmark problems using the simplest 6-bit multiplexer version. In this problem, there are 6 features, each of which can have a value of 0 or 1. The first 2 features are address bits, having possible combination of values of 00, 01, 10, and 11. These point to one of 4 other register bit positions. Depending on the position the first 2 address bits are pointing to, in this case pointing to the second position, the outcome for that instance is determined by the value of the bit at that position. So in this case, the green circle has a value of 1, thus our outcome is 1. This pattern holds for all other instances generated for this problem. The problem is epistatic because we need 3 of these bits' values at once to determine what the correct class outcome is. And it's heterogeneous because it can be a different combination of bits, always the first 2 address bits, and then 1 of the other 4 register bits. This problem is also convenient because we can scale it up in complexity, each time adding another address bit to the problem. We can see how this problem grows in complexity, all the way up to the 135-bit example that requires us to find 128 separate combinations of 8-way feature interactions. And there are a total of 4.36 times 10 to the 40 possible data points that we can construct for the 135-bit problem. For some quick context, the 6-bit problem on its own is a difficult problem for a lot of basic machine learning algorithms to solve, including decision trees, logistic regression, and naive Bayes. And to date, I believe that only learning classifier systems are the algorithms that have been able to solve up to the 135-bit multiplexer problem. Going back to our ExSTraCS algorithm, when we published the second paper, we demonstrated ExSTraCS solving this 135-bit multiplexer problem with a very high degree of accuracy. And when published, it was the first time ever that this problem had been solved directly. So the point here is that rule-based machine learning and learning classifier systems have the potential to tackle extremely complex patterns in data while still fundamentally being a much more interpretable kind of algorithm since it gives solutions in the forms of groups of if-then rules. We can see just from these experiments with multiplexer problems that these algorithms are able to detect both complex interactions and heterogeneity, which many other machine learning algorithms will struggle with. To help facilitate the characterization of heterogeneous patterns in data, we've recently developed a pipeline called LCS-Dive, designed to be used in association with the ExSTraCS algorithm. Here's a preprint on this pipeline if you want to read a little bit more. Basically, this pipeline takes output from the ExSTraCS algorithm, including the rule population and attribute tracking scores, and it seeks to automatically determine how to best cluster instances in the data, and again, this is done as a way to help characterize heterogeneous subgroups. As an illustration of this pipeline in action, here we've run it on the 6-bit, 20-bit, 37-bit, and 70-bit multiplexer problems. You can see in these illustrations how the attribute tracking scores reveal the unique set of features that together allow the algorithm to make an accurate prediction of outcome. As we can see, the address bits are always important, but in different subgroups of instances, a different register bit is important. And this is true for all of these examples. Another thing we've worked on is making evolutionary rule-based machine learning algorithms and learning classifier system code in general accessible and available for use and download. Given scikit-learn's popularity, we've taken to implementing a small variety of learning classifier systems, including the well-known ExSTraCS algorithm, and a basic educational learning classifier system, which is most similar to UCS, a supervised learning classifier system that was proposed a number of years back. This code was paired with a textbook written by myself and Dr. Will Brown, who'll be giving the last part of this tutorial. Note also that we've created a scikit-learn version of ExSTraCS, making it much easier to apply any of these rule-based machine learning algorithms in comparison to other standard machine learning algorithms available in scikit-learn. You can find a paper about our adaptation of ELCS as a scikit-learn package in this paper. And furthermore, if you want to try out LCS-Dive, you can find it on our GitHub repository here. The last thing I'm going to talk about is a new automated machine learning analysis pipeline we've developed called STREAMLINE. This project actually started with our desire to more easily compare our rule-based algorithms to other standard cutting-edge machine learning algorithms out there as a way to demonstrate just how effective these rule-based methods can actually be. This project is now 3 years in the making, and I'm really excited to share this code with you. Currently, this pipeline is only set up for binary classification, but we're currently extending it to multi-class and regression outcomes as well. In a nutshell, STREAMLINE is an end-to-end pipeline for machine learning predictive modeling in a rigorous and transparent manner. It automates many of the aspects of a data science pipeline, including exploratory analysis, data processing, feature processing, modeling, summarizing analyses, conducting significance analyses, generating publication quality figures, and even making a summary report as a PDF file. We designed it to adopt best practices in machine learning analysis, and it offers users flexibility, customizability, and expandability for the future. We also designed it to specifically deal with a variety of common data challenges we've described earlier in this talk, but also to scale to bigger and bigger data analyses, and ensure that we're able to detect and interpret complex associations in data, including both epistasis and heterogeneity. If you want to read more about STREAMLINE, the first publication on this software has recently been published, and you can read more and try it for yourself by going to this GitHub repository. Without getting into too much detail, here's a schematic giving an overview of what STREAMLINE does. Starting with one or more datasets provided by a user, STREAMLINE automatically conducts data exploration and processing of the data, including some basic cleaning and feature engineering. Next, it applies k-fold cross-validation partitioning, and then subsequently imputes missing values in the data and transforms it using a standard scaler. Next, we apply two feature importance algorithms, one that's great at detecting univariate effects and another that's great at detecting interactions. Using both of these algorithms, we apply feature selection, removing features that are very unlikely to be predictive of outcome. Next, STREAMLINE moves on to machine learning modeling itself, and the user can apply all or any number of these 15 algorithms included in STREAMLINE, all of which are scikit-learn compatible. STREAMLINE automatically conducts hyperparameter optimization using the Optuna package. It trains a final optimized model. It estimates model feature importance values, and it conducts a comprehensive evaluation of all models. Then it moves on to post-analysis, where it summarizes results, generates figures, and applies statistical comparisons. If multiple datasets were run at once, STREAMLINE also compares performance across all algorithms and datasets, with visualization and statistics to back them up. Then if the user has further holdout data, STREAMLINE allows the user to easily apply all trained models to that replication data for another round of evaluation. This, for example, allows a user to train a model perhaps in one hospital system and then see how well that model performs in a second, third, or fourth hospital system. And lastly, STREAMLINE generates a PDF summary report highlighting major findings. As a quick highlight, you'll notice that among all these machine learning algorithms included, we have the 3 scikit-learn compatible rule-based machine learning algorithms we've previously developed, including ECLS, ExSTraCS, and of course ExSTraCS. As mentioned, STREAMLINE generates a wide variety of data summaries and visualizations to provide transparency throughout every phase of the analysis pipeline, all the way from exploratory analysis to model performance summaries to feature importance evaluations, and even interpretable model visualizations for decision trees and genetic programming. In this first paper on STREAMLINE, we evaluated the framework on some basic simulated datasets. First, simulated genomic benchmark datasets created with the gametes software, having simple univariate effects, additive effects, epistatic effects, and heterogeneous effects, and showing how a variety of algorithms performed on each of these datasets. Note how on easier datasets, most machine learning algorithms are performing about the same, and only when we move on to additive combinations, epistasis, or heterogeneity do we start to see a big separation in how different algorithms perform. Also of note, ExSTraCS is the green line here, and in these simulated runs, it's working as well or better than all other machine learning algorithms included. Going back to our multiplexer examples, here we're running STREAMLINE on the 6-bit through 135-bit problems. To save time, we only gave STREAMLINE a limited number of samples for the 135-bit multiplexer problem, too few for it to accurately solve the problem. However, I will point out that algorithms like decision tree, naive Bayes, and logistic regression fail to solve any of these problems, and only our rule-based ExSTraCS algorithm is still performing well even when tasked with solving the 70-bit multiplexer. Now, to be fair, it's important to know that ExSTraCS won't always be the best performing algorithm on every single dataset, and part of the reason to use STREAMLINE is to avoid making the assumption about what's the best algorithm to use before you've even applied it to data. When using STREAMLINE, you'll always get the perspectives of multiple machine learning algorithms, all applied in a fair and comparable manner, to help find out which algorithm is going to perform best for your dataset. And our newest version of STREAMLINE is set up so that you can add any other scikit-learn compatible machine learning algorithm to the suite of existing STREAMLINE modeling algorithms. I'm going to end by pointing you to a demo of STREAMLINE, allowing you to easily run different machine learning algorithms, including ExSTraCS, our rule-based machine learning algorithm developed for biomedical data science. Head to the STREAMLINE repository on GitHub for more information. But in summary, STREAMLINE provides 4 different run modes for different levels of user coding experience. You can run a very quick demo in Google Colaboratory without any knowledge of coding at all, or you can run it in a Jupyter Notebook on your local PC, or run it from the command line, as well as in a computationally efficient manner on a parallel computing cluster. STREAMLINE comes with a demo dataset taken from the UCI repository, specifically the hepatocellular carcinoma data. We chose it because it's small, with 165 instances and 49 features. It involves a biomedical classification task discriminating between patients that survived or were deceased after a year. And this small dataset exemplifies many of the data considerations or challenges we've mentioned, such as it includes mixed feature types of categorical and numeric. It has some missing data values of about 10%, and it includes class imbalance, with 63 of the subjects being deceased and 102 having survived past a year.